let's recall what we're trying to do with series. So we're going to start off with a sequence. We're going to form another sequence of partial sums. Then we're going to take the limit of those partial sums as n goes to infinity. If that limit goes to a number, we'll say the series converges and the series has some, okay, that number, which we'll call S. Now, in the real world, you're probably not going to have a formula for S. So what you would do instead is you would just try to approximate S using your partial sums. Now, that's only going to be useful though if you have a formula that lets you estimate the remainder. So the remainder is going to be the difference between your actual sum and your partial sum. Okay, so you can think of that as if your partial sum is your guess at the actual sum, the remainder is going to be the error in your guess. Now, let's run through some of the series where we can do this. For the geometric series, we have an actual formula for the sum. So in this case, we can get a formula for the remainder precisely. If we're using the integral test, okay, we're not going to have a formula for the remainder, but we can put a bound on it. So the idea is if you want to get your sum within some degree of tolerance, there's a rule that lets you get as close to your sum as you want. Now, for alternating series, it's going to be the same idea. We're not going to be able to get the exact remainder, but we are going to be able to bound it within some number. So let's take a look at that test. So what's our procedure going to be? I want to get my partial sums within epsilon of my actual sum. And epsilon is going to be a small number. So what will we do? I'm going to find an n such that a sub n is less than epsilon. So we have our a sub n, okay, it's going to be decreasing and its limit's going to go to 0. So somewhere, if you give me an epsilon, which is a small number, I can always get under that epsilon with an a sub n. Then the rule is going to be, okay, if we take the nth partial sum for that n, then the actual sum minus our partial sum, okay, absolute value, is going to be less than a sub n plus 1. Now, since the a's are decreasing, a sub n plus 1 is less than a sub n, so this is going to be less than epsilon. So that's our test for finding an estimate of the error for an alternating series. Now, where does our estimate come from? Let's take a look at the picture for a convergent alternating series. So here, we're going to put n along the x-axis, and then along the y's, we're going to have our partial sums. So if our first term is a positive, then we're going to have the odd partial sums along the top, the even partial sums along the bottom. And then through the middle is going to be our actual sum. Now, if I want to go from one partial sum to the next partial sum, the way we do that is by adding or subtracting the next a. So let's take a look. If I'm at the partial sum for 2n minus 1, how do I get to the partial sum for 2n? Well, in this case, we're going to subtract off a sub 2n. So that's going to be the distance here. Now, if you know the difference between s and s 2n minus 1, okay, put an absolute value, that distance is going to be less than our a sub 2n. So that means our remainder here in absolute value is less than a sub 2n. So that's 1/2 of our estimate. Now, if we look at s sub 2n, I want to go to s sub 2n plus 1. How do we go there? Then in this case, we're going to add a sub 2n plus 1. So that's going to be the distance here, from here to here. Now, you'll note the difference between s and s sub 2n. Okay, put that in absolute value, but you don't need to here. Okay, that's going to be our remainder. That difference here, okay, or distance, is going to be less than a sub 2n plus 1. So that's going to give us the other part of the estimate. So if we put that all together, okay, we'll get rid of the reference to odd or even. What we'll have is, okay, is that our remainder, okay, an absolute value, so it's going to be our actual sum minus our capital N partial sum. It's going to be less than a sub capital N plus 1. let's look at an example. So consider the alternating series. Sum as n goes from 1 to infinity, minus 1 to the n plus 1 over n. So that's just going to be 1 minus a half plus a third minus a quarter, and so on. Here, a sub n is going to be equal to 1 over n. So if we take the limit of a sub n as n goes to infinity, we get 0, and this is going to be a convergent alternating series. Now, we're going to pick an epsilon, so I'll take 0.0001, 1 over 10,000. Then we want to find the n so that the nth partial sum is within epsilon of our actual sum. Now, what do? We're looking for n such that a sub n plus 1, which is equal to 1 over n plus 1, is less than epsilon, okay, or 0.0001. So we're trying to solve this inequality. I multiply both sides by 10,000 n plus 1. That's going to give me n is greater than 999, or n equals 10,000. And you could use any n bigger than 999, and you'll get the same idea. Now, if we take the 10,000th partial sum, it's going to be the first 10,000 terms. It's going to be 1 minus a half plus, and then all the way up to minus 1 over 10,000. Okay, you want to do that on a computer. It's going to come out as 0.6930972. So the claim is this partial sum is going to be within 0.0001 of the actual sum. Now, in this case, we can get the actual sum. That's going to be natural log of 2. Okay, we'll see later on how to get that. So in this case, we'll go to our calculator. We'll have the actual sum is 0.6931472. So if I take the absolute value of the remainder when n equals 10,000, we're going to get s minus s sub 10,000. Okay, that's our absolute value of the remainder. And then I'm going to get 0.00005. And that's definitely less than our epsilon.